Let's get going. So I think we only have 3 full problems to do today here. And these were all past AP exam questions. They like to hide them at the end, like question 5 or question 6. So like on the non-calculator portion. All right, so the Maclaurin series for ln of 1 plus x is given by that. So they're giving you the series so you didn't have to memorize it, even if that is one you memorized, great, but you didn't have to. On its interval of convergence, the series converges to ln of 1 plus x. Let f be defined by this function. So it's close to that, but we've got an x over 3 and another x out front. Write the first 4 non-zero terms in general term. So there's an and here. So 2 things from the Maclaurin series of f. So, I mean, here are the 1, 2, 3, first 4 terms and the general term. So what it's asking us to do is figure out how do these 2 guys relate to each other? How do we transfer from this guy to this guy? Well, it looks like this x is now changed to x over 3. And then we're multiplying the whole thing by x. So first I'm going to plug in x over 3. So everywhere I've got an x in this, I'm just going to replace it with x over 3. First guy, not much difference there. Second guy, we've got x over 3 squared over 2. There is a minus out front. And then we've got x over 3 cubed over 3 minus x over 3 to the 4th over 4 plus dot, 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 plus negative 1 to the n plus 1 x over 3 to the n over n plus dot, dot, dot. So that's with the x plus 3. Now we need this extra x. Ta-da. All right, now I'm not going to leave it like that. I'm going to pretty it up some. So let's see, we've got x squared over 3 minus, this is going to be x cubed. We've got a 3 squared and a 2. Just going to write it like that. Then we're going to have x to the 4th. We're going to have a 3 and 3 to the 3rd. Minus, I mean, we could put this all together if we wanted to. I don't know if it's going to really make a difference. This was a 4 here. So that's going to be x to the 5th. We've got 3 to the 4th times 4 plus dot, 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 plus negative 1 to the n plus 1. We're going to have x to the n plus 1, 1 from that, n plus the n from that. We got an n on the bottom, and we've got 3 to the n. Now, if you worked out these numbers, more power to you. That's perfectly fine. That's 9 times 2 is 18. 3 to the 4th is 81. 81 times 4, 324-ish. Yeah, that seems right. 18 times, yeah, that'll work. Does it matter which order we applied the x and switch to x over 3? It kind of does, yeah. You got to do the inside first. So like this is actually getting plugged in for the x because this x is now being replaced with x over 3. So that's got to go inside here. And then this is outside the ln. So afterwards, in the end, you're going to multiply the whole thing by x. But that's in the end. If you did it first, you're getting an extra 3, I think, on the bottom because you'll have x over 3 to an extra exponent, and that'll throw things off. Yeah. So that's our guy there. There's our answer for this guy right there. Part B, determine the interval of convergence for the Maclaurin series of f, show the work that leads to your answer. All right, so for part B, I'm just going to write out what the sum was. And we got it basically from the general term right here. So that's what we need. There's our general term. It's going to start when n equals 1, right? Not 0 because we have 0 on the bottom, but 1. Let's see, we've got n equals 1 to infinity. We had negative 1 to the n plus 1. We had x to the n plus 1. We have 3 to the n and an n down there, I believe is what we had for our series. To get the interval of convergence, what we probably want to do, since it's not geometric, it's got this extra n down here and this n plus 1, x plus 1 up there, is we want to do the ratio test. So the limit as n goes to infinity of negative 1, and then we're going to add 1 to the n's here. So this is going to be n plus 2, x to the n plus 2, 3 to the n plus 1, and then this will be n plus 1. We've just added and plugged in n plus 1 essentially everywhere. And then it's divided by this whole term. So since it's already a fraction, we just flip it, multiply 3 to the n, negative 1 to the n plus 1, x to the n plus 1. All right, now the negative ones are going to go away because the absolute values. Some 3's are going to cancel. We've got 1 3 left on the bottom. Some x's are going to cancel. We've got 1 x left on the top, and we've got an n and an n plus 1. So really, we're getting n over n plus 1. We've got a 3 down here on the bottom, and we've got an x left right there. So absolute value of x, because that's the only place where the absolute value matters. This limit right here, as we go to infinity, this is just going to be a 3 on the bottom and a 1 on the top. So it's going to be 1/3. So it's going to be the absolute value of x over 3. We need that to be less than 1 for it to converge. All right, so we move the 3 up. We get the absolute value of x is less than 3, or -3 is less than x is less than 3. Now we need to check those two endpoints to see if it does converge at -3 and 3. So we're going to plug each one of them in here. So for x equal -3, we get the sum from 1 to infinity, -1 to the n plus 1, -3 to the n plus 1, 3 to the n, and n. So what's going to happen here are the 3's are going to cancel out. And this is going to be another -1. These two are going to always cancel out. Like they'll be both negative or both positive. So we're just going to get like this is the sum of 1 over n, which diverges. So we don't want to include that. Now we try the other endpoint, the 3. All right, now this one's not going to cancel out that -1 to the n plus 1. All right, and I guess there was an extra 3 here on the top, but it's still going to, I guess, 3. There we go. Because there was n plus 1. But still, it's going to diverge. The 3 we could write out front if we wanted to. Anyway, so then the same thing's going to happen here. So the 3 to the n is going to cancel. This is going to cancel. And it's going to leave us with 1 3 on top and n on the bottom. But it's this alternating n plus 1. So we could say it's 3 times the sum of -1 to the n plus 1 over n, which converges. It's an alternating series. All right, so we can just say it converges. I don't think we have to actually do the alternating series test here, but it converges. The limit goes to 0. It's greater than 0 if we take the absolute value. It converges conditionally if you want, but it works for our purposes here. So the interval that we're going to get is going to be from -3 to 3, like that. Including that, not including that. You could also write it -3 is less than x is less than or equal to 3, like that. Either one of those is fine. Should have had a little more room here. Part C, and I guess I'll change colors here. Let P sub 4 be the 4th degree Taylor polynomial for f at x equals 0. Use the alternating series error. So that would be the 5th degree term in absolute value to approximate the upper bound for the difference between those two guys at 2. So at 2. So that means we're going to plug in 2. So let's see. Do we have a 5th degree term already? We do. Here's our 5th degree term right there. Cool. That's what we're going to plug into. And this was 3 to the 4th down here, if I remember. All right. So that we want to say, let's see if I can just write it up here. So the absolute value P sub 4 of 2 minus f of 2 should be less than the absolute value of that 5th degree term, which was negative. And then it'll be 2 to the 5th, 3 to the 4th times, what was it, 4 or 5? Was it 4, I think. Let's go back and just look. Yes, 3 to the 4th and 4, x to the 5th, yes. All right, so that's our guy right there. So let's say the negative is going to cancel out because we're in absolute value. 2 of these 2's are going to cancel out. So we're going to get 2 to the 3rd over 3 to the 4th, which is 8 over 81. And there we go. Done. I'm pretty sure that's all we need to show. All right, so let's see. What do we have here? So we got that, we got that, we got that, we got that. First 4 terms, that works. Check. General term is that. Yeah, we just had it down the line, but that was what we had. So both points there. Cool. Next one, let's see. Sets up the ratio for that. We did that. Computes the limit of the ratio. We did that. Radius of convergence. Yeah, we got the 3 over there. Yep. Considers both endpoints. We did both of those. And so, yep. Notice it says just considers them. You don't even have to get them right, apparently. You just have to consider them for the point for that. So you just got to plug each one of them in. And analysis and interval for the convergence. So this is where we have to get them right. So this is where we have to say that this diverges because it's the harmonic series, and this one converges by the alternating series test. And then our interval we got as that. All right, but you didn't actually have to show the steps for all the alternating series tests. You just have to say alternating series tests, which I think it just has to be decreasing after a certain point, always positive, and the limit goes to 0, I think was it. We got 2 more people that have shown up since we started here. Make sure I write their names down so I can add them to the spreadsheet here. There we go. All right, and there was our answer for that one. So uses the 5th degree term for the error. Yep, we did that. We used the 5th degree term, and we got our answer. There's our answer. What cancels out in that to the n plus 1 or 3 to the, okay. So on that one, we had -1 to the n plus 1. We had -3 to the n plus 1. We had 3 to the n, and we had n, right? And you want to know what canceled out there? So this I can split up to -1 times 3. And then I've got -1 to the n plus 1, another -1 to the n plus 1, and then we've got 3 to the n plus 1 over 3 to the n and n. So this and this can cancel, and there's just 1 3 left over on top. These two, we can add these two exponents together because they're both -1. So we get -1 to the n plus n is 2n. 1 plus 1 is 2. Or we can say 2 times n plus 1. But if we do that, and let's see, there's a 3 here. If we do that, you notice this number is always even. So -1 to an even number is going to be positive. Or you can be like, oh, it's -1 squared, which is 1. And then 1 to the n plus 1, which is always just 1. So this is just 1. So we can just say it's 3 over n. So that's how these two guys cancel out for the person who asked that direct message. Yeah. -1, if they're both to the same exponent, they're going to cancel out. All right, next question. This one was odd. When I saw this, I was like, ooh, they were defining this recursive relationship with the, I wrote you down. I haven't added you to the spreadsheet yet because I'm not going to flip over the spreadsheet in the middle of the presentation here. So a function f has derivatives of all orders for -1 to 1. So for x in those sections there. Yeah, it's good. The derivative of f satisfy the conditions above. The Maclaurin series of f converges for f within that interval. And f of 0 is 0. F prime of 0 is 1. And then like the second derivative at 0 is -2 times the first derivative at 0. And then the third derivative at 0 would be -3 times the second derivative of 0. So it's what we call a recursive relationship. It depends on the earlier things. All right, show that the first 4 non-zero terms of the Maclaurin series are that, and write the general term. All right, well, we need to just list a whole bunch of what happens with derivatives here first. So we got that so far. Now the second derivative. Well, it's going to be -2, because it's the second derivative, and then the first derivative at 0, which we said is 1. So that's -2. The third derivative at 0 is, well, it's going to be -3 times the one less derivative at 0, which we just said was -2. Right? That's what we got. This is -2. So it's -3 times -2. It's 6. And we want the first 4 non-zero terms. So this one's 0. So we've got 1, 2, 3. We need one more. So the fourth derivative at 0 would be -4 times f triple prime at 0, which we just calculated to be 6. So -4 times 6 is -24. All right, now hopefully when we write out these terms, we'll be able to see a pattern, and that'll help us get the general term part. So if we write out these terms, the first term is 0. So 0, x to the 0, plus 1 times x to the first over 1 factorial, minus 2, right? We're getting the negative from the 2, x squared over 2 factorial, plus 6x cubed over 3 factorial minus 24 x to the 4th over 4 factorial. Oh, it's the one less number here. Yeah, I was doing it backwards. I was like, this is canceling out completely. That's not working. It's good of them to tell us that because then we can cancel that out. Yeah, it's the one less number here. I didn't notice that. So this would be -1. And then this would be -2 times -2. It would be 4. Go back and change all this. And then this would be -3 times 4 would be -12. Fixed it. All right, so this was -2. Yeah, that'll still work. This was +4, not 6. It's good of them to have the answer here. Otherwise, we would have screwed that one up. And then this one was the -12. There we go. Plus ... All right, so let's see. We're getting x minus, these are going to cancel out completely, x squared plus, well, this isn't going to cancel out quite completely. Why do we still have a 4 here? That's not going to cancel out completely. That's going to be 2/3. I need the 2 to not be here. Oh, this was 1. Did it again. Really messed this one up twice. Just try this all over again. So did that, rid of that, rid of that, rid of that, and we'll try this one again. All right, so we're getting -1 here. And then times 1 is -1. So we get -1. Okay. -1, let's see, this is the second one. So this is -2 times -1 is 2. This is going to be -3 times 2 is -6. Okay, so 1, 2, -6. There we go. Third time's a charm. So we're getting x squared over 2 factorial is just 2. This is going to be x cubed over, let's see, 3 factorial is 6. 2 with the 6 leaves us with that 3. Minus, okay, the 2 and the 3 will cancel. We'll be left with a 4. There we go. That works out. Now, can we figure out the general term here? So we've got x to the n. We've got an n on the bottom, like it's the same number. And we've got a negative sign. So is it -1 to the n? Well, if we plug in 1, nope, that doesn't work. So we'll just do n plus 1. There we go. There's our general term. So put a plus ... There's our Maclaurin series for that. Determine whether the Maclaurin series described in part A converges absolutely or converges conditionally or diverges at x equals 1. Explain your reasoning. All right, well, for part B, at x equals 1, we'll have the sum from, let's see, it looks like we're going to go from 1 to infinity because we started x to the first and not the constant term. We've got -1 to the n plus 1. We're plugging in 1 here, so that'll be 1 to the n over n. 1 to the n is just 1. We don't need to worry about that. So we've got -1 to the n plus 1 over n. So this is an alternating series. So this converges. All right, now we wanted, though, not if it just converges. We want, does it converge absolutely? Does it converge conditionally? Or does it diverge? Well, it doesn't diverge, right? Because the -1 gives us alternating series. But if we take the absolute value of this, we look at the sum from 1 to infinity of just 1 over n, that diverges. All right, so since the absolute value diverges and the irregular guy converges, that means that this guy converges conditionally. All right, so it converges conditionally. And there's me explaining my reasoning. Since this is the absolute value, if you want, you can write, the sum of the absolute value of -1 to the n plus 1 over n equals that diverges. There we go. I suppose if I'm going to put indices, I got to keep putting indices. All right, so there's my justification. I've got my reasoning is that the absolute value diverges, the regular series converges, so it converges conditionally. All right, part C, write the first 4 non-zero terms and the general term for the integral of that series. All right, well, G of x equals the integral from 0 to x of, well, let me just write in those first four terms. So my first four terms were those guys and the general term, so and that guy. So we've got x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus dot, 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 plus x to the n over n and negative 1 to the n plus 1. And we're integrating with respect to, ooh, that's a problem. Anybody notice what the problem is? I made a boo-boo. Yeah, the variable, good. So I can't have the same variable here and as this as I have in here. So I need to change all of these guys to a different variable, and or I can change the other guys outside to a different variable. Like I could change this and this to a different variable, but I'm just going to change the inside guys, and it looks like they said to use t. So I'm just going to use t here. So t, 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 dt. All right, so now if I integrate this, I know a plug-in 0 is going to give me 0. So just integrating and then switching it to x. So this is going to be t squared over 2 minus t cubed over 3 times 2 plus t to the 4th over 3 times 4 minus t to the 5th over 5 times 4. I know I did that one backwards. I don't know why. And then this one's going to be t to the n plus 1. The negative 1 is not going to change. And then this will be n plus 1 times n. And then we're going from 0 to x. If we plug in x, we're getting x squared over 2 minus x cubed over 6 plus x to the 4th over 12 minus x to the 5th over 20. So there's our first four non-zero terms, plus dot, dot, dot. And now our general term is x to the n plus 1, negative 1 to the n plus 1 over n times n plus 1. All right, and there's my general term. So I got both of those things. Here we go. Part D. Should have really put more space here. Let p sub n of 1/2 represent the nth degree Taylor polynomial for g about x equals 0. So it is this same Maclaurin polynomial because it's x equals 0. So it's the same thing. Evaluated at x equals 1/2, where g is the function defined in part C. So g is this guy. Use the alternating series error bound to show that. All right, so this is 4th degree, p sub 4, 4th degree. Here's my 4th degree term. So that means the error is the 5th degree term. So this error, let's just write it out, p 4 1/2 minus g of 1/2, the Taylor polynomial, or Maclaurin polynomial in this case, which is the same thing, minus the g value, the actual function value, will be less than the absolute value of 1/2 plugged into this next term, the absolute value of that next term. So we get negative 1/2 to the 5th over 20. So the negative is going to cancel out since it's absolute values. 1/2 to the 5th is going to be 1 over 32. And we get a 20 down there. 30 times 22 or 20 is 1 over, is that 640? And then we're showing that it's less than 1 over 500. Well, this is bigger than 500, so that's less than 1 over 500. Done. All right, like 1,000th is less than 1/500th. There we go. 1/640th is less than 1/500th. All right, so scoring on this one. So it took me like 3 tries here, but I eventually got this one right, looks like. Yep. So we found the next derivative. So you're given points for those values. There's 1 point. Verify terms. So yeah, we plugged in and we got that. Yep. And we got the general term. Yep, we got that. Converges conditionally with reason. The series does not converge absolutely because the harmonic series diverges. Yep, we said that. The series alternates with terms that decrease in magnitude to 0, and therefore series converges conditionally. I don't know. I mean, we said alternating series test, but we didn't say that it decreases and the limit goes to 0. We might get the point for that one. We didn't need it on the last one, but apparently we needed it on this one. I don't know. Nitpicky. All right, but now moving on to the integral. So interesting. We get 1 point for 2 terms. I guess that's the first 2 terms. That's this guy and this guy. 1 for the remaining terms, which I guess are the next 2 terms. And then 1 for the general term. All right, well, we got all the terms, so I guess we'll get all the points there. So that's all 3. And then this guy, let's see, alternating series decreases, blah, blah, blah. The alternating series error bound is bounded by the next term. So there's the next term. And so we just plug that in there. And, well, we could probably stop here and just say that that's less than 1 over 500. There we go. Hopefully that would be some easy points for some of you. Maybe not an easy 9, but an easy 7 or 6 or 8. I don't know. All right, last one here. So the function f has a Taylor series about x equals 1 that converges to f of x for all x in the interval of convergence. It's not really telling us much. It is known that f of 1 is 1, f prime of 1 is negative 1/2, and the nth derivative of f at x equals 1 is given by, all right, so it's given us another one of these recursive relationships. Write the first 4 non-zero terms and the general term of the Taylor series about x equals 1. So now this time, remember, it's a Taylor series. So we're going to always have an x minus 1 to the n. All right, so that's the difference between the Taylor and the Maclaurin. The Maclaurin, we just get x to the n, x to the first, x to the second, x to the third. Taylor, it's centered at x equals 1. So we got to remember the x minus 1 in there. All right, so the first thing we need to do is we need to get the first 4 non-zero derivatives. So f of 1 is 1. Well, that's good. That's a non-zero. F prime of 1 is negative 1/2. Okay, that's 2. F double prime, let's see if I can get this right this time, of 1 is negative 1 to the second. Then we've got n minus 1, so 2 minus 1 factorial over 2 to the second. Right, 2 to the n, yep, second derivative. Okay, so this will be, well, that's positive 1. That's also 1. So it looks like 1/4. All right. F triple prime of 1 is going to be negative 1 to the third. So that's going to be negative 3 minus 1 factorial. So that's 2 factorial, which is just 2. And we get 2 to the third. So we're getting negative 2 over 8, which is negative 1/4. All right. And that gives us 1, 2, 3, 4 terms. All right. So that should be our first 4 non-zero terms. So our first term is just 1. Our second term is minus 1/2 x minus 1 to the first over 1 factorial. Next, we've got plus 1/4 x minus 1 squared over 2 factorial. And then we've got minus 1/4 x minus 1 cubed over 3 factorial. Plus dot, dot, dot. Now we need the general term. Now it's just a matter of, do we recognize a pattern? Well, we could probably just use that to help us get our pattern. All right, so our nth term, our nth derivative, right, so 0, 1, 2, 3, will be negative 1 to the n minus 1 factorial over 2 to the n. Then we're going to have an x minus 1 to the n over an n factorial plus dot, dot, dot. All right, now the n minus 1 factorial, the n factorial, those can cancel out some if we wanted to. And these two things could just become an n on the bottom. Right? N minus 1 factorial, n factorial. Yeah, that just gives us an n on the bottom. All right, so we got an n and a 2n on the bottom like that. So there's our general term. Part B. The Taylor series for f at x equals 1 has a radius of convergence of 2. Find the interval of convergence, show the work that leads to your answer. So they're already telling us that the radius is 2. So that means it saves us a little bit of time. So for part B, it's getting us all the way to the absolute value of x minus 1 is less than 2. It's getting us to there. It basically is what that's telling us with that. And it is still centered at 1, so don't forget it's x minus 1. So that means negative 2 is less than x minus 1 is less than 2. And if we add 1 everywhere, we get -1 is less than x is less than 3. So that means we need to try these two endpoints now to figure out our interval. So first we try -1. So if we try -1 in, again, this is our general term. So we're going to have the sum n equals 0 to infinity, right? We start with the 0 term here, x to the 0. And we've got, let's see, -1 to the n, x minus 1. So -1 minus 1 to the n, 2 to the n, and an n. All right, and then we want to know, does that converge or diverge? Well, let's see. This is going to be -2 to the n. So we can say that's -1 to the n, another -1 to the n, and a 2 to the n, right? Because this is just -2 in here. So we'll split the negative sign out and the 2 out. We've got 2 to the n and an n. Well, these 2 to the n's are going to cancel now. And these these -1s to the n are also going to cancel, right? We get -1 to the 2n, then they would just both become, or they'd either both be -1 or both be +1, but we get positive either way. So this just becomes the sum. I don't like that I have from 0, and I've got an n on the bottom. We'll just go 1. I don't know. Maybe that'll work. Really, we only care about what happens with 1 over n, though, which diverges. All right, it's the harmonic series. All right, for the other endpoint, x equals 3, we've got -1 to the n, 3 minus 1 to the n, 2 to the n, and an n down there. All right, so this is going to be 2 to the n. It's going to cancel out completely with that down there. So we're just left with -1 to the n over n, which converges. It's alternating. One over n is decreasing, and the limit of 1 over n as n goes to infinity goes to 0. I don't remember what else we had to say. 1 over n is greater than 0. I don't remember if positive was part of just the integral test, the alternating series test, but either way, it converges, and the -1 diverges. So we get -1 is less than x is less than or equal to 3, or -1 to 3, including 3, not including -1. Yeah, I don't think positive was required because we've already taken the absolute value of it for the alternating series test. So there we go. Part C. The Taylor series for f at x equals 1 can be used to represent f of 1.2 as an alternating series. Use the first 3 non-zero terms of the alternating series to approximate f of 1.2. I can, because I'm going to have to go back really quick anyway, because I need the first 3 non-zero terms. There's my first 3 non-zero terms. So let's see, we've got 1 minus, and then it was 1/2. 1.2 minus 1. Is it over 1 factorial? Yeah, over 1 factorial. So we don't need to put that. Plus, and then it was 1/4, right? Yeah. 1.2 minus 1 squared over 2 factorial, which is just 2. So those are the first 3 non-zero terms. So this is be what we call p sub, well, it's degree 2, p sub 2 of 1.2. All right, and we want to estimate this. So this is 1 minus 1/2 of 0.2 plus, it's going to be 1/8 of 0.2 cubed. I hope this was a calculator one. I don't feel like working that out. Is that 1/5? This is going to be 1/25 squared. You're right. I saw that and I thought 3, but yeah, it was squared. Here we go. So let's see. It's going to be 1 minus 1/10 plus 1 over 8 times 25 is 1/200th. Yeah. So that's 1 minus 0.1 plus what is 1/200th as a decimal? 0.005. This 1/100th would be that. 1/200. Yeah, I think that'd be that. So this is 0.905, I think. I don't know. I mean, we could always pull out the calculator. I guess this was calculator. Show that the approximation found in part C is within that of the exact value. All right, well, then we would look at the next term here. So for part D, we want to say that the difference between the second degree polynomial at 1.2 minus the actual function value at 1.2 is less than the absolute value of the third degree term. So we look at the next term, which is this guy. So that's -1/4. 1.2 minus 1 to the third, there's to the third, over 3 factorial. And we just want to work that out. So the negative is going to cancel. We're going to get 0.2 to the third, 4 times 6, so 24. So is that 1/5 to the third? So that's 24 times 125 down there. Yeah, this must be a calculator one. Or really, we just have to show that that's going to, this number here is more than 1,000. And it is. 1 divided by 24 times 125. Oops, parentheses. 1 divided by parentheses 24 times 125. There we go. Lots of zeros. So let's see, we're going to have 0.000333. All right, which is less than 0.001. Hey, that's what we wanted. All right, now let's see. Did we do that right? Or did I do that right? You guys didn't say anything besides the squared, which good for you. All right, so what do we got here? So we've got our first two terms. So that was this and that. Yeah, we had those two. Then we had our third term. That's another point. That was nice. And then our term after that. Yeah, I think we had that. And then our general term. All right. I think we had all that. And so all 4 points there. Identifies both endpoints. So we got -1 and 3 as the endpoints. Yep, we got that. Analysis and interval. So we plugged in each one of them. So this one was the harmonic and it diverged. This was the alternating. I guess they just accept that the alternating harmonic series converges without any sort of justification. And we get the interval that we got. Okay, so both points there. Approximation. Hey, that's what I even got working it out in my head. All right, but yeah, it was just the plugging into the first 3 terms there. And then the error formula. Yeah, they're not so hard, guys. So that is what we got there. 1 over, I guess, 2 to the 8th times 3 times, so that is 24 times, yeah, that was what we got there, which is less than that. So so we got the error form. I guess this is the error form. So that's 1 point. And then that other point there. So we got them all. And that is the end of that.